My name is Sebastian Chinoya, and I attend University of Texas at El Paso. And my name is Rodriguez, and I attend University of Texas at El Paso.
I'm Alexander Quesada. I attend Lehman College from the City University of New York.
I'm Shikha Rao. I attend BITS Pilani Hyderabad campus.
Cool. As a quick introduction, for our REU here at Lawrence Tech, we are developing, analyzing, and evaluating self-drive algorithms using real street legal electric vehicles in real time on a predefined environment based on line following and lane centering algorithms. So short and sweet, that is what we're doing today. So moving on to the novelty, what we developed through lane following algorithms that operate under all kinds of weather conditions, all kinds of weather conditions that were present during our testing. And we tested the algorithms on a real self-driving electric vehicle. And we also combined the contour block detection and offline methods to develop an algorithm for lane following. Cool. The testing equipment we did use was, first of all, the modified Polaris. Modified Polaris Gen 2, max speed of 20 miles per hour, and also a range of 20 miles. It's a sponsored data speed drive-by-wire system, a turn radius of 150 inches, width of about 405 feet, and a length of eight and a half feet. Sorry, and also a Mako G319 camera. Most important part about this, ROS integration, a resolution of 2064 by 1544, and a max frame per second of 37 frames per second.
That's the environment that we're using. That's parking lot edge here at the LTU University campus.
Okay, so now for our code architecture. So it is worth noting that we printed this RQT graph from a Frostback. So instead of connecting to the Frostback, this will be connected to the drive-by-wire system installed on the Polaris Gen 2 vehicle. So our core architecture works by so we have several nodes here. This line follow node is called the same. It's the same structure for all three algorithms. So the line follow node does one thing only. It takes the camera image, it checks where the lane lines is, and based on that, it computes a yaw rate so the vehicle knows where to turn. And then it publishes that to the control unit. The control unit handles the vehicle speed and turning. It's like the one node that controls the movements of the vehicle. It can decide whether or not to set the yaw rate values from this node based on other messages it gets from the other nodes. So then here we have the yellow line node. All this node does is it detects this yellow line over here, and it does that actually by taking the camera image and getting like a specific region where it will only see like just part of the yellow line, like around there, like in a rectangle. It does that by first it converts the image to HLS image, which stands for hue, saturation, and light values, and we pass it like we pass the parameters specifically for yellow. This parameter can vary depending on the lighting conditions. So if it's very sunny, we might have to increase the saturation in the light. Or if it's overcast, we have to put like very low values. So we have to play with that depending on the lighting conditions outside. And like once it sees the yellow line, it doesn't like send a message right away to the control unit. It first waits. It actually first takes like the contour of the contours of yellow pixels. So like the number of yellow pixels in the frame it sees in the region of interest. If it sees like above 6, if it computes the area of yellow pixels, the number of yellow pixels it sees, and if it sees more than 600 yellow pixels for 7 consecutive frames, then it say, okay, that's the yellow line, and we'll send a message that I saw the yellow line to the control unit, and the control unit knows that after the yellow line in parking lot H, we have to make a dead reckoning turn. So we have like an algorithm to automatically do that turn since we cannot see the yellow line. It's pre-programmed. We have one more node that actually is very important. We call it the SDT report, and SDT stands for speed, distance, and time. All that node does is keeps track of the time the vehicle is in motion, the distance it has traveled, and the speed is going. So the yellow line actually takes the time from the SDT report to count, because we have to like adjust some parameters, because when you would make the reckoning turn like this, so if we go back to the parking lot H, so that would be over here. Wait, no, that's wrong way. So like around here, so if he's making this dead reckoning turn, right? When you would make it, we'll see this other yellow line, and we interfere with the yellow line detection. So like what I did was like I put a 30 seconds cool down, like when he's making this turn here, to not look at other yellow lines until the 30 seconds pass, and then so it will keep looping. Okay, thank you. Yeah, and once you see the yellow line, you will drive up to the yellow line, stop for 3 seconds, and then continue doing the definitely turning like that. It would look. And then it will let the control unit, this will handle doing the death reckoning turn. So all these nodes are communicating with each other. That's for the core architecture.
Moving on to the filters and the ROI. Due to the difficult course of lighting conditions that we were faced with a cluttered image, cluttered and noisy image that made it difficult to detect the lane lines. So the colors that we were interested in looking at were whites and yellow. We did this by converting the image to an HLS color space to select only these colors and combine them into a mask. After filtering, we were left with an image that contained only either white or yellow. However, the image remained very noisy. So this problem was minimized as much as possible through the implementation and the modification of OpenCV functions such as canning and range and a custom adjustable white balancing filter. In addition to filters, we applied a region of interest, which was added to the image to crop out any unnecessary visual information. This was done through the utilization of an empty array with 5 points that was used to plot a polygonal mask to boost efficiency. And one important thing to note was that this ROI was different for each algorithm based on the area that we wanted to focus on. Here you can see the ROI being plotted. That's given us this image right here, so you can see there's very little noise. And over here we have our detection for yellow, which as Alexander was explaining before, just detects yellow and does our death reckoning check. And for algorithm 1, we called it our blob/shifted line following algorithm. And this algorithm was the simplest, but ultimately it allowed us to familiarize ourselves with the environment and the challenges that would be present over the course of testing. So this algorithm utilizes a proportional turn rate that is calculated by finding the centroid of the largest contour that's generated from lane lines and the center of the camera in ROI, and then functions from the OpenCV library. Through rigorous testing, we found that although this algorithm is reliable, with smooth curves at low speeds, once the speed increases and the curve gets sharper, the accuracy of this algorithm decreases. So this algorithm was ultimately used as the base for other 2 algorithms. And here you can see some images of simulation, and you can see the differences in the detection of the lane lines based on the noise and the overall quality of the image. So here in simulation, it's almost perfect because there's no disturbance. But in real life testing, you can see that the lane line isn't great, and that's because of the saturation of light.
Our second algorithm uses Hoff lines for line detection, and it also uses a combination of contour for some of them. So we experimented with like 4 different combinations of algorithms with line detection and lane centering, and we ultimately found that Hoff lines followed by contour detection work the best, and for lane centering, offsetting the Hoff lines work the best. It worked much better than averaging the center middle lane line and then going off with that. And we tested them in simulation and in real-time environment. And in simulation as well as in real life, the last algorithm is the one that worked the best. It works really, even though it jitters in simulation at higher speeds, it does not jitter in real life and works really smoothly in when testing it on the actual course. And this is an example of the average center lane line lane centric method with offlines. And this does not use the blob detection on the center lane line. Instead, it uses the second coordinate. So when we plot a line, we use two coordinates. So it uses the second coordinate, the one at the top, and it takes the x coordinate from that, and it automatically calculates a yaw rate from that. So that's what is being used here. And over here, this is the one that's actually working in real life in our on our vehicle. That's the second algorithm that we've been testing. That plots a half line and offsets it, and then there's contour detection on top of that. And this was working really smoothly. It was going at a really high speed to of about 6.7 miles per hour. Yeah, the next algorithm that we have is the spring lane following. This is based off of Professor Nick Paul's spring-based algorithm that was written in C++. This is implemented in Python, and we also made it a little faster so that it's able to follow the lane at 20 frames per second. And it uses the spring. It's based off of spring force, and it's generating a bunch of rays to push the car to the center of the lane. So that's how it's working. And we also realized out of all of the three algorithms, the turns, like based on the course, in the course environment, we realized that some of the turns were harder than the others. So for Hofflines, when it was going on the outer lane, the turn 3, the turn over here, turned out to be the hardest. Whereas when we were using the blob algorithm, and when we were going in the inner course, the turn 2, the turn over here, that turned out to be the hardest. So we realized that for different algorithms, different locations on the track were more difficult than others. And values.
So this is evaluating the fastest, the smoothest, the most reliable algorithm out of all of them. So after intense testing, the algorithm that managed to reliably almost work most of the time, as long as the weather conditions were playing nice with us, was Offline. So Offlines, we actually got it to make 2 full laps at 6.7 miles per hour, which was very surprising to us. So this algorithm is sort of introduces like the novelty to this paper. We consider it like a minor improvement because we are combining blood detection and Hofflines together to form this algorithm. So we're building on what we had before. We're adding Hofflines to it, and it makes up for the weaknesses that plain blood detection does. Because with plain blood detection, since the lane lines are not the smoothest, are not connected, are kind of broken up, that interferes a lot with the with blob detection because the center of the blob is always changing. So the peak is always turning rapidly, which makes which makes the vehicle a little jerky. But with Hoffline, since we're looking for specific slopes, we're always looking for this one line, and that one line it doesn't move. It's stable most of the time, and that's why like even at highest speed, it's only looking for one line, and then it's showing like another line which we call fictitious based on how Dr. DeRose calls it, and we have the algorithm follow that middle line, and because that middle line is like being artificially drawn to the screen, the color is always the same, so the blob detection works really well on it. And that's why the algorithm is able to so smoothly work even at faster speeds. Of course, given the lighting conditions are good. It was also the fastest, the smoothing, the overall best algorithm for us for both inner and outer.
So these are during the official runs. These are the successes that we had, and the weather conditions varied a lot during the same time. It was overcast sometimes, rainy sometimes, sunny sometimes. So even with all of these weather conditions, we were still able to have successes with all three of the algorithms that we implemented. And there were a few errors, but we realized that the HOF did not have many errors at all. So that's how we concluded that HOF was the best algorithm for out of all of them, because there aren't any line touches or lane departures, but there are still a few of the errors. It's still not a perfect algorithm, and of course it can be improved, but it's much better than the blob and the spring algorithm that we were doing. One more thing that we noticed that was that spring algorithm was working much better for the inner lane of the course rather than the outer lane. In the outer lane, it was having a lot of lane departures, and there were infinite number of lane touches and lane touches. But for spring in the inner, there were no errors, and it was also really smooth. And we think that it could go at a much higher speed as well. Then fails during the official run. We had two failures. The reasons for the failures was that so the offline failed on the outer course. The reason for the failure was that it was going at a very high speed then, and the sunlight suddenly changed from sunny. It suddenly changed from overcast to sunny, and the camera couldn't adjust fast enough, so it lost it at one of the turns. And for spring, the reason that it failed during the outer lane was because of the dead reckon. Was because of the dead reckon term. And
Well, now I'd like to I'd like to discuss some environmental challenges first. What we faced out there during our official test runs. So first one is you can see up here at the top left is going to be broken or like dirt patches on our actual lane lines. This would break up our tracking for our lane lines. This would make it very inconsistent. A quick solution that Dr. Chung actually came up for us with us would be the strip of reflective white tape we would place along, securing along the dirt patches or broken lines. This would allow us to keep a more consistent and brighter white line. The one that we didn't expect to happen to us exactly would be on official test day. It was overcast and then it turned into downpour on rain. This caused two problems. The first one being, as you can see in this picture, reflective ground. The puddles would leave us with the reflection of the white clouds above, messing up our white blob detection and our lane tracking. Another one was the constant downpour onto our windshield, which obviously would mess with the camera behind the windshield. And then another challenge was the tree. Near the course, this would leave a big blob of shadow, and this the drastic light change between like bright white to the dim light would not allow the camera to pick up the lane lines. Solution for that for us, we use dynamic reconfiguration with our HLS values. We adjusted light. We would while during the run we'd adjust it through dynamic configuration. And then not lastly, but the one on the far right corner, we have the yellow parking lane lines near our white lane lines. This would interfere with our yellow detect. This would cause premature stoppage of the course because the camera would pick up the yellow lane lines and think it will going for the hard reckon turn. Our solution for that, we developed an ROI and are able to crop the image so that it wouldn't see anything outside of our lane lines. And then one last one that is not on here. At the beginning of one of the courses, we had two white lines on the side on the beginning of an outer test. We were able to block those with like objects we found by. Those are a quick solution on official testing. Also, challenges that aren't labeled here that aren't environmental, but they were coding actually challenges software is simulation versus actual in real life testing of simulation. Everything symmetrical, as you can see back in the courses, if you can remember it. There is a symmetrical circle. Yeah, you can bring it back. Cool. As you can see on this is like our simulation. Everything's symmetrical, everything's even, no issues there. So our programs, our algorithms would run perfectly at high speeds in simulation, but when we brought them out to the actual course, as you can see, the environmental challenges that I just discussed interfered with the performance. So it was kind of a yes, it would work in simulation, and we go out to test it, and then we have to change up all our values all over again.
Yeah, so now for the works human drivers, so for the most part, the human drivers managed to somewhat keep within the speed limits, but we did have like major speed violations. And also like it's not it's not very consistent. A mysterious driver over here or went quite fast, almost 50 miles per hour. So definitely over our speed limit. And then next slide, please. And now when we compare it to the algorithm, it's much more consistent. For as you can see, it's like there are many more lines because of it's doing it like almost it's doing very fast. If it adds very minor adjustment, it does it very fast. So like there is much more like threaded. But it's also more consistent in we don't have any speed violations because most of the algorithm could not go that fast to begin with. The Hotline was the only one which managed to go to 7 miles per hour, but unfortunately I forgot to record back for that one. We might have like a graph to show here.
Just to recap, we proposed and implemented 3 different lane following algorithms using computer vision and testing them on an electrical vehicle in a control testing environment. And the real testing environment had sharp curves, poor road conditions, unclear, and narrow lane markings and dynamic light conditions, which did mess with the detection of lane line. We evaluated human driving and the algorithms for self-driving vehicles using a custom performance evaluation function. And we analyzed this and compared them to come up with our data. And ultimately, our most reliable algorithm overall ended up being our Hotline implementation. Thank you. Oh, actually, lastly, I would like to thank Dr. Chung, Dr. D. Rose, Dr. Siegel, Joe, Mark, Professor Nick Paul. Thank you all for like this opportunity through this REU. We've all, I believe, we agree that we learned a lot.
Yeah.
And we're very grateful. Thank you.
Thank you so much.
Thank you so much.